All right, this is Honors Algebra 2 Pre-Calculus. We're doing Chapter 7, Section 1 of Algebra 2, and this is our first video, Introduction to Polynomials. So the fancy math definition of polynomials is that a polynomial function, which we're going to call p of x here, right, is essentially the sum or difference of a bunch of powers of x, where the powers are essentially whole numbers, right? So starting at 0, n would be 0, 1, 2, 3, 4, etc., etc. And those powers of x, right, have coefficients, and the way we mark those coefficients is that the the power x to the n has coefficient a sub n, and the power x to the n minus 1 has the coefficient a sub n minus 1, and the power where there's no x at all, the x to the 0 would just be called, the coefficient would be a sub 0, and the power where we have an x to the first, that would be a sub 1 as the coefficient, etc. Okay, so so what makes this a polynomial, again, is that these powers of x, right, n and n minus 1 and n minus 2, etc., all of those powers are whole numbered values of, or whole numbered values, right? So, so what does this mean? So a polynomial is an expression that has a sum or difference of x's to whole numbered powers, meaning that the following are not polynomials, okay? So the reason this is not a polynomial is the root, right? So that's why this one's not a polynomial, right? This one's not a polynomial because of the division of the x stuff. In fact, the top is a polynomial. The bottom is also called a polynomial, but together, when you divide them, it's not a polynomial. This one's not a polynomial because this is a 4x to the negative second, so not a polynomial. This one's not a polynomial because this is exponential, right, where x is the exponent, not the base. Exponential, right? And these are not polynomials because the powers are not whole numbers. So these are not whole numbers. The same thing with this one, right? That x to the negative second was not a whole number. So that's why those are not polynomials. One of the reasons we want to be able to identify polynomials is that they're really happy, easy functions to do math with. So we're going to really enjoy when we get polynomials in math. Sometimes we're going to see other things like exponentials or things with roots, but polynomials are really nice, happy functions. So polynomials are classified in two main ways. The first is by degree, meaning the highest power of the x, which is a bit of a lie. If we're talking about p of x, and we could talk about what polynomials look like in multiple variables, but for our purposes in this course, we're pretty much talking specifically about polynomials in terms of one variable. So by the degree, which is the highest power of the variable, it doesn't have to be x, right? And by the number of terms which are separated by addition and subtraction. So let's walk through this terminology. The reason we want to make sure we learn the appropriate vocab is that sometimes we're going to be handed a problem where a function is described to us as something like a quadratic trinomial or a linear binomial or whatever, and we need to understand what those words mean, because sometimes something will be described, but we won't actually be able to see the function. So first, by number of terms. So notice that terms are separated by addition and subtraction. So in this first example, 3x squared is what we call a monomial, meaning one term. There's the only term, right? A binomial, right, means two terms. So there's the 2x. A subtraction symbol separates that from the 18. That's two terms, binomial. A trinomial has three terms. You can see the 3x to the fourth, the 12x, and the 17 are all separated by addition or subtraction. That's three terms. And anything with four or more we usually just call a polynomial. To be clear, all three of these are also called polynomials. Even monomial, which might seem a little counterintuitive because poly means many and mono means one. But these are all, so the generic term is that these are all polynomials, but the specific term based on the number of terms would be monomial, binomial, or trinomial. And you've seen that a little bit when we talked about factoring, right? We learned how to factor special binomial patterns. We learned how to factor quadratic trinomials. So speaking of quadratic trinomials, here are terms based on the degree of a polynomial. So if a polynomial has a highest power of x to the 0, then it's just called a constant. So keep in mind that that 5 is actually a 5 times an x to the 0, which is why the degree would be 0, and that's called a constant. Something with the highest x power of 1 would be called linear, right? So this is a 12x to the first minus 17, so that's called linear. Something with the highest x power that is squared would be called quadratic, right? Something with the highest x power that is cubed is called cubic. Something with the highest x power that is a 4 is called a quartic, right? Like a quarter, if that helps you remember. Like when you cut things into fourths, you use a quarter, right? Like that's a quarter of something, or a quarter of a dollar, right? Anything after 4, I would say it's easier to just say polynomial of degree blank. So for instance, 2x to the 10th minus 3x to the 6th minus 2x plus 5 would be a polynomial of degree 10. And certainly there are words for things past the fourth degree, but it's just easier in most cases to refer to the degree after you pass 4. So standard form of a polynomial has the powers descending, which if you look back, this was standard form, right? N is the highest power, x to the n. This is 1 less than that, right? And this is 1 less, and then 1 less, and so on, etc., until you get down to nothing. So standard form of a polynomial is to have the powers of the variable descending. All right, so let's classify each polynomial by degree and number of terms. The easiest way to do this is to start by putting this polynomial in standard form. So for a, I'm going to recognize that the 4x to the fifth would be the first term, right? The 2x to the third would be the next term, and the 3x would be the last term. So I see that it's a trinomial, right? And I could actually, there is a word for fifth, you could say quintic, right? But I'm going to say that this is a trinomial of degree 5. Now, if you wanted to use the word quintic, you could, but to be honest, I would say anything after 4, it's easier to just say of degree 5, so I would suggest that. If we put this one in order, right, the trick here is that the cubes actually combine. So I get a 3x to the fourth plus no x cubes, right, plus a 5. So this right here would be a quartic, right, because the highest degree is 4, and binomial because it's got 2 terms. So quartic binomial, right? So quartic refers to the x to the fourth, and the 2 terms is where I get binomial. All right, go ahead and try that with P1. You can pause me if you want. When I put this in order, I get a negative 2x cubed plus an x squared minus an 8x plus a 4, right? So that makes this a cubic, right? And it's just going to be a cubic polynomial because it's got 4 terms. So cubic polynomial, right? It does have, so if you really wanted, it has 4 terms. So there, you actually can call it a quadrinomial, but most of the time after 3 we just say, so quadrinomial. After 3, most of the time we just say polynomial, right? So you can get away with, if the terms are greater than 3, you can just say polynomial. But again, if you really wanted, it's a quadrinomial. If we go ahead and combine these terms here, right, I have a negative 6x to the fifth. It seems like these are both cubics, right? So I get a plus 2x cubed plus 2, right? So this is a trinomial of degree 5. Again, if you want, instead of saying of degree 5, you could say quintic, but most of the time after. But I would say anytime the degree is greater than 4, it's okay to say of degree blank. I mean, it's never wrong to say of degree blank anyway, like of degree 2, of degree 3. It's just much more common for us to use the words, for instance, cubic and quartic and quadratic. All right, so moving on. Evaluating polynomials. So this is merely an extension of evaluating functions that we covered in a previous chapter, right? Basically, when you evaluate a polynomial for a given x, you need to plug that x into all of the spots in the polynomial. So when we plug in f of negative 2, I'm going to need to make sure this is a 2. Negative 2 has to be cubed, right? Minus a 3, a negative 2 that's going to be squared, plus a 5 times that negative 2 minus a 6, right? This is going to be a 2 times a negative 8 minus a 3 times a positive 4, minus a 10 minus a 6, right? I seem to get an awful lot of negatives. So I seem to get negative 16 and negative 12, and then another negative 16 for the 10 and the 6, right? So that should be a negative 32 and another negative 12. So I think we get a negative 44. Yeah, so there we have it. All right. If I plug in f of 0.5, and I kind of strayed a little bit, but if we plug in f of 0.5, again, you could totally use a calculator to do this if you want, right? It would be fine if we want to quit out for a sec. It would be fine to do 2 times this negative 2 cubed minus 3 times a negative 2 squared plus a 5 times a negative 2 minus a 6. That'd be absolutely fine. And hopefully we get a negative 44. And then if you want to hit second enter, you can put in a 0.5. Again, you can do it by hand. Sometimes it's going to be useful to do stuff by hand. Sometimes it's not. I can just put in a 0.5 everywhere I saw a negative 2. Right, and hit enter, and I get negative 4. Right, so if I do this, right, if I plug this in, if I do 2 times this 0.5 cubed minus a 3 times a 0.5 squared plus a 5 times a 5 minus a 6, right? We can see from the calculator that I get a negative 4, right? If you wanted to do this by hand, this is a 1/2, right? So you'd get 2 times 1/8 minus a 3 times a 1/4 plus a 5 times a 1/2 minus a 6, right? And if you wanted to clean this up, that's a 1/4 minus 3/4 plus 5/2 minus 6, right? So this is 1/4 minus 3/4 is negative 2/4, so negative 1/2 plus 5/2 minus 6, right? That's a 4/2, so that's a 2 minus 6, which sure enough gives me a negative 4. So it doesn't matter to me how you get there, but that's the idea, is that you're plugging in. All right, let's go ahead and try P1. You can certainly pause me if you want to. All right, so when I go ahead and plug in 2 here, right, this is going to be negative 4 times a 2 to the 4th plus a 2 to the 3rd plus a 5 times a 2 squared minus a 2 plus a 3, right? So this is going to be negative 4 times a 16 plus an 8 plus a 5 times a 4 minus 2 and a plus 3 is a plus 1, right? So I'm going to get that this is a negative 64 plus an 8 plus a 20 plus a 1. If I put all the positives together, which is sort of the easiest way to do this, I get a positive 29 and a negative 64. So that should be a negative 35. Yeah, that checks out. So I get a negative 35. Now again, if you want to put that in your calculator, you certainly could, right? So this is negative 4. I have a 2 to the 4th plus a, and there's a reason that I'm typing this in. Like, I know that I could do 2 to the 3rd in my head, but the reason I'm typing it in is because if I were going to type it in, it makes the most sense to type in exactly what the whole expression is, so that then I can just second enter and do the same thing with the negative 1 in a sec. So let's double check that it's right. So negative 4, the 2 is to the 4th, the 2 is to the 3rd, a plus 5, 2 is to the 2nd, a minus 2 and a plus 3, and I hit enter, and hopefully we get a negative 35. And then if I hit second enter, right, I can do the same thing. Oh, my bad. Second enter, I can do the same thing with a negative 1. The only trick is that since it's a negative 1 now, I'm going to have to insert a number. So second insert, I need to insert that negative and then turn it to a 1 from a 2. And then here, I've got a negative and then second insert 1, right? Because I'll type over if I don't. And here I have a negative and then second insert 1, right? And then this is going to become minus a negative 1. So if you just wanted to make it a plus 1, you certainly could, and then hit enter, and I get a 4. So that's fine, right? But again, it's good to be able to evaluate this stuff by hand if you have to. I would point out that negative 1 is actually one that's easier to evaluate by hand than by putting in the calculator. I'm just trying to give you options, right? So if I were talking about evaluating this in by hand, I think this is a lot easier because really I just have to understand that powers of negative 1 that are even come out positives. This is going to be a negative 4 times a positive 1, plus this will be a negative 1, right? Because negative 1 cubed is negative, right? Plus this will be a regular 5, right? This will be a plus 1 and a plus 3. Well, this is a negative 5 and a plus 5, so they're just gone, and I just get the 1 plus 3, which is the same 4 that I got when I typed it in the calculator. Again, it's the same concept as evaluating functions you've done before. It's just that sometimes you'll see a lot more x's now. All right, so adding and subtracting polynomials is pretty intuitive. You basically just add and subtract the like terms, right? So you're basically going to clean up anything that needs to be distributed, right? And you're going to combine like terms, which are terms that have the same degree of the same variable, right? So here there's nothing to distribute, so I'm just going to rewrite this as a negative 2x squared minus a 3x cubed plus a 5x plus a 4, and then this is all going to stay the same. I'm just going to line it up conveniently. So this will be a negative 2x cubed, which I lined up with the other x cubed, a plus 7x, and a minus 6. So when I add them all together, right, I get negative 2x squared minus 5x cubed plus a 12x minus a 2, and then I write my answer in standard form by putting the x cubed first minus the stuff that's x squared, and then the stuff that's a regular x, and there we have it, right? So that's my answer. Let's try a P3, same idea. Again, this is a plus sign, so there's nothing to distribute. So you're just adding them. So a 2x to the 4th plus a 4x cubed plus a 5x minus a 2, right? So I have a negative 2x to the 4th. I have a minus 7x squared, which doesn't line up with anybody, so I'm just going to put them over there, plus an 8x minus a 10. So when I combine my like terms, the x to the fourths go away, right? I get a 4x cubed, a 13x, a negative 12, and a minus 7x squared, but I don't have that in standard form, so my final answer is going to be a 4x cubed minus a 7x squared plus a 3x minus a, 13x rather, minus a 12. Now, an interesting side note is if I had spotted that I was missing a squared here, right, there's no x squared, I could have left a convenient space right here, and then that would have allowed me to line the 7x squared up to the right space already. It can be easier to put your stuff in standard form before you combine it. It's up to you. You just have to end up with it in standard form. Okay, so when there's a difference, right, the only thing with a difference is I have to distribute that negative. And the same thing would be true if I put like a number in front of one of the functions, right? Like if there were a 2 here, I'd have to distribute it. So I'm going to get that this is a 6x cubed minus a 6x squared plus a 7x minus a 1, and then I'm going to distribute that negative. Now, it's up to you. You can write straight across if you want. I really like writing things vertically because I think it's a little bit easier. It doesn't matter to me. Like, if you just want to write this straight across, you certainly can. I'm going to go ahead and do this negative 3x cubed plus a 5x squared plus a 2x and a minus 8, and I'm going to go ahead and add straight down, right? I distributed that negative and I add, so I get a negative 9x cubed minus an x squared plus a 9x minus a 9, and that's already in standard form, so that's my whole answer. Same thing here, right? We're going to distribute this negative, right? If we have a number in front of our parentheses, we'd have to distribute that too. So I'm going to have a 3x to the third minus a 12x squared minus a 5x plus 1, and when I distribute the negative, I get a plus x squared, right? Because that'll line up with the x squareds. I get a minus 5x and a minus 8. So when I add straight down, right? I'm going to get 3x cubed minus 11x squared minus 10x minus 7, and that's my final answer. All right, so let's talk about the basic graphs and general shape of polynomial graphs. Okay, so in a bit of non-mathy terminology, we can refer to bends in graphs as what's called U-turns, right? So you see that in a parabola, and we'll talk about that in a sec. A basic x squared parabola has one U-turn. In fact, all parabolae have exactly one U-turn. The degree of a polynomial is linked to the number of possible U-turns, but you can't identify the number of U-turns just from looking at the degree. So you can in the case of something that's squared, and we'll talk about that in a sec. So for example, lots of cubics have 2 U-turns, but the simplest cubic, y equals x cubed, doesn't have any. So what we can say is that a polynomial of degree n has at most n minus 1 U-turns. So a linear graph has no U-turns. It has no turns at all. It is just a line, right? A quadratic graph will have exactly one U-turn, and you can picture that because you can think about what quadratics look like, but right here you see how that's a U-turn. It turns. The graph seems to turn, right? Graph seems to turn. That's one U-turn. As the degrees get higher, it's a little bit harder to know just from looking at a graph or just from looking at an equation what the graph's going to look like. So here are a couple cubics, and you can see I graphed them on the calculator. This is a cubic that has 2 U-turns. 1, 2, right? The graph's going along. It goes on a U-turn. So think about it like you think about if you were driving, right? Graph goes along, U-turn, right? Same thing here. This graph has 2 U-turns. 1, 2, right? This graph has no U-turns. This graph has no U-turns, right? All of them are in an S shape, right? Now, I get that sometimes it's a backwards S, but you get the idea, right? A quartic graph, which has degree 4, can have as many as 3 U-turns, right? So if n is 4, it can have up to n minus 1 U-turns, but it certainly doesn't have to. So you can see this one has 1, 2, 3 U-turns, right? This one has 1, 2, 3 U-turns, right? So that's the most. But this one just looks like a weird kind of fat parabola, right? Like it looks wider. It doesn't have any U-turns. So this one has 3 U-turns, 3 U-turns, 0 U-turns. Or sorry, 1 U-turn. Come on, brain. 1 U-turn. Right? Just the 1 U-turn. It looks like a parabola. This one had 2 U-turns. Right? This one had 2 U-turns. This one had 0. Right? Those had 0 U-turns. They were just an S-curve. So having the basic idea of what a graph looks like is really helpful. It's useful to know that a cubic pretty much always looks like this if it's a positive cubic, or this if it's a negative cubic. And sometimes it has a more pronounced U-turn. Sometimes it just looks like this and like this, right? Quartic graphs look like W's or M's if the leading coefficient is negative. So you can see all the ones I drew you here look like W's, but certainly a quartic could look like this, right? So that could be a quartic. It looked like an M. All right, so in E5, we're going to graph a function on a calculator, and we're going to describe its general shape. So let's go ahead and graph this. So 3x cubed minus 5x squared minus 2x plus 1. All right, let's see what that looks like. All right, so I'm going to zoom 6 because who knows what window I was using before. Hey, there we go. So this is exactly what I'm expecting out of a cubic, right? So I can actually, we'll take a quick little screenshot of that because we have the luxury of doing that on a computer. Yay. All right, so this looks like this, right? So if I were going to describe this, right, I would say that this graph has an S shape, which I already could have guessed because it's a, oh, my bad, because it's a cubic, right? Has an S shape and it has 1, 2 U-turns. So it has 2 U-turns. Now, when we get to calculus, we're going to learn some other ways to refer to those U-turns. We're going to learn, in fact, we'll actually learn that soon. We're going to learn that we have what are called local extrema or local maxes and local mins. We'll learn that in Algebra 2 as well. But we're going to spend a lot of time talking about these important values where there are U-turns when we get to calculus. If I graph the other one, I'm expecting this to be a W, right? I'm expecting this is either going to look like this or it's going to look like one of those long parabolae. Like that's what I'm expecting, right? So this is what I expect based on my knowledge of an x to the fourth, right? So let's go ahead and put that in, right? So I have an x to the fourth minus an 8x squared, and double check that we have that right, and then hit graph. Yep, and there's my w, right? And I can see, it's hard to see the actual U-turn, so I might want to change my window and go a little bit lower, right? I want to try negative 15 maybe, and graph. Nope, not far enough, so we'll try negative 20, right? If I want to see those U-turns, I know they're there, but if I want to see them, there we go. So, so there's my graph, right? So this is a W shape. I didn't know if it would be a W or one of those U's without actually graphing it, right? I was expecting, same thing when I saw the x cubed, I was expecting either something like this or something that was just sort of the straight shot up, right? That was my expectation. So, so look at this, say, cool, it's a W shape, and it has 1, 2, 3 U-turns. All right, and that's all we're looking for when we talk about describing the general shape of the graph, right? So let's do one more. You'll do a P5, and that'll be it for this video. Now, I look at this negative cubic, and I say, cool, I'm expecting something that looks like this, or that has the like straight shot and looks like this, right? So that's what I expect before I graph it. I look here and say, okay, cool, I'm expecting a W or one of these like sort of awkwardly wide parabolae, right? So that's what I expect. So it's a good idea to be able to expect that before you actually graph it. Like it's nice to have a rough idea of what something's going to look like. So let's go ahead and do, we'll do this one first, right? So we have negative 3x to the third minus a 2x squared plus a 2x minus 1. And do remember I adjusted my window, so I'm going to zoom 6 just to see what happens. All right, so sure enough, that's exactly what I expected, right? Like it's good idea to know in your head, hey, this is what I expect, because if I hadn't seen that part of the graph, or if I'm expecting a W and I don't see a W, I see something that's part of a W, it might mean I need to adjust my window, right? So sure enough, I've got an S shape, and I've got 1, 2 U-turns, right? Again, it's really helpful to have a rough idea of what things look like because it makes the process a lot easier. So I'm going to go ahead and turn this to a 2x to the fourth minus a 3x squared. Oh, that's not what I wanted. We did not want a logarithm. Minus x plus 2, and then we'll go back and double check that I got rid of anything extra I need. So 2x to the fourth minus 3x squared minus x plus 2. We hit graph, see what our window looks like. Hey, there we go. And sure enough, it is that W I was expecting. You're not always going to get a W, but I was expecting a W, and that's what I got. So there's 1, 2, 3 U-turns, right? So this is a W shape with 3 U-turns, right? And that's a really generic way to describe the graph, but that's sort of the idea. And that is section 7.1.